Hey everyone, all right, we're going to do the real notes for exponential applications. So we're going to take situations and create equations, do a table, and graph. Okay, so we're going to pick them apart to give some information and show information. So for the first one, Mr. Quinto bought a new car at a cost of $25,000 in 2005. The car depreciates approximately 15% of its value every year. So part A, write an exponential function to model the value of his car and define your variables. So the first thing we're going to do is define our variables, which means what is X and what is Y. So in this problem, we have money and we've got time. And if you remember anything that we've talked about this year, you know time is always your X. Okay, so this is number of years. And then our Y is the value of the car. Okay, so when we write our equation, we're going to write it in this little space up here. Equation, okay, it's going to be of the form y equals a times b to the x. So our initial value here, okay, our initial value is a, that's the original cost of the car. And then we need to find our exponential base b. Okay, so we have this rate here. Okay, we have this rate. We know that it's decay because it's depreciating. So we're going to take this information, we're going to take 100% minus 15% and get 85%, which 85 as a decimal is 0.85. So our B here is going to be this 0.85. So our equation is going to be y equals 25,000 times 0.85 to the x. There's no spot for you to put the equation, so just put it up there. Okay. So in part B, is this an example of exponential growth or decay? We just said decay because of the depreciating. So decay because the problem states, or let's say uses, problem uses, my pen's not working, uses depreciates. Okay. So we're going to use our equation to help us create our table. So if you remember from the other day, this 0 right here represents your initial value. Okay, so the initial value of the car was $25,000 because that's how much you originally paid for it. So now we're going to find after 1 year how much the car was, after 2 years how much the car was, 3 and 4. Okay, so in our equation, 25,000 times 0.85 to the first, remember the x is up there, we're going to just do these calculations. So I want you to go ahead and do those on your own really quick. All right, so here's what we should have in our table. So the first one, we have 21,250. For year 2, we have $18,062.50. Year 3, we have $15,353.13. And year 4, we have $13,050.16. So remember, your rounding rules apply here. So we're going to take this information and we're going to graph what's happening, because even though we stopped at year 4, we stopped here with x equals to 4, it doesn't mean that the car stops depreciating. The car will never stop depreciating. Okay, so we're going to set up our graph. So remember, we have our origin here, 0, 0. Our x values are number of years. Okay, so we have 0 to 4 years. So I'm going to go ahead and I'm going to just skip a line between so I have some space. So 0, 1, 2, 3, 4. And then remember your Y values are the value of your car. Okay. So if it starts at 25,000 and it's decreasing from there, if you look at all your values, it's decreasing in value. The highest value we need is this 25,000 right here. Okay. So what I'm going to want to do is just make sure that when I do graph, when I do put my points in for my y-axis, that I can get to 25,000. So I think I want to start at 5,000 right here. Okay, that means every other one, so that would be 10,000, 15,000, 20,000, and the very top line should be 25,000. Again, you can set up your graph how you want, just make sure all the information is there. So 0, 25,000, okay, that's our y-intercept. So then we have year one is 21,250. So really in between here we have my pen will work. We have $2,500 is separating everything. So if we go every other, let me show you what all these should be. So this is 22,500. So it kind of gives you an idea of that where that 250 should be. It should be somewhere in the middle here. Okay. It's not gonna be perfect, but it'll be there. So then year two is a little over 18,000, which means that it should be roughly somewhere in there. Year three, we have 15,300. So it's going to be just a little bit above 15,000. In year four, we are a little above 13. So just a little above that 12,500. We are going to connect our dots. And it should be relatively curved because this is an exponential function. And then we'll put an arrow at the end because this is going to continue to decrease. Okay, so that's what our graph looks like. So then now part E, if the car continues to depreciate following the same percentage rate, what would the car's value be now? Okay, so our equation, I'll just write it down here so I don't have to scroll up. So this was our equation. Okay, and so it's asking for now. So now is 2021. This problem started us at 2005. Okay, so we need to go from 2005 to 2021. Okay, so we need to count how many years that is. It looks to be it's going to be 16 years. Okay, because 5 plus 16 gives you 21. So the x value we're going to plug in is that 16. So y equals 25. Okay, sorry, my pen's not really working right now. 0.85, and we're going to raise it to the 16. So if you do the calculations on it, we should get a dollar amount of $1,856.28. Okay. All right, so that's our answer for that. So for part F, if the car continues to depreciate following the same percentage rate, what would the car's value be in year 2099? So we need to go from 2005 to 2099. So that x value, our years, is going to be 94. Okay, 94. So we have y equals 25,000 times 0.85 raised to 94. Okay, so when you do your calculations, we should get 0.005, we'll just round right there, 0.0058. Okay, so this means this car is worth, so it's not even worth 1 penny, because 1 penny is 0.01, and we're not going to round to 0.01. Like, this is our answer. That's the dollar amount that it's worth. So it's not even worth a penny. Okay. So that's the kind of stuff that we're going to be doing. The hardest part is making sure you're graphing correctly, because I think everything else you guys are really strong in. Okay. So, we'll do one more, but I think I'm going to have you do most of it on your own. Okay, so just be ready. So number 2, the population of a popular town of Mathopolis is 2003. It was estimated to be 38,000 people with an annual rate of increase, in parentheses, growth of 2.7%. So we can answer one of these questions already without having to do anything. We know that this is exponential growth because it says growth. Okay. So it says growth. The other indicator, why my pen is doing that. And increase. Okay. So we'll go back to part A, write an exponential function to model the situation. So it's saying M of A represents the total population, and A is our number of years. So really, this is our Y value, and the number of years is our X value. So when we go to graph, hopefully that won't be confusing for you. So first things first, what is our A? Okay, identifying what your A is should be 38,000. And then B, our exponential base, it says it's increasing at a rate of 2.7%. So we're going to take 100 plus 2.7, and we get 100.27, which as a exponential base is 1.027. So M of A equals 38,000 times our exponential base raised, and we're going to put A because that's what it's asking for, but this is really our X value. Okay, so that's our equation for part A. So using that equation, I'll write it down here. So M of A equals 38,000 times our exponential base, 1.027, raised to the A, which again is our X, and this is our Y. You need to fill out your table. So go ahead and fill out your table now, and then come back and check your work. All right, so take a minute and check your table. All right, so make sure all those values are what you have. Check your rounding. Keep in mind this first value right here is your y-intercept and your initial value. So that's the smallest number you should have because we have increase. We have a growth, exponential growth model. So now we're going to talk about our graph, and I'm just going to kind of get you started. So remember that our independent variable is our years. There we go. And then this one on the y-axis is our population. Okay. So again, we're starting at 0. We're going to skip because we have room 20, 30, and 40. So if you have room, you can go every other. So then these would be going by 5. So 5, 15, 25, and 35 if you needed it. So on the left side, we need the maximum we get to, because we're going to be drawing a line. We're going to be drawing a line with an arrow. We need to make sure that we have room for all of these values. The highest value is year 40 with 110,000. So we need to make sure we show room for that. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we could start at 20,000 here. I wouldn't recommend starting right at 38,000. I would give yourself some room. So we're actually going to go up by 20,000, and I'm not going to skip lines here. Okay, so 60, we've got 80, we've got 100, and we've got 120, and that should cover it. We just don't have room to skip. So my first point is really, really, really close to 40,000. It's 0 and 38,000. Then 10 is really close to where 50 would be, so about halfway between, because it's 49,600. 20 is at about 64,000, so close to 65. So it's going to be a little bit closer to 60 because we're going up by 20,000. 84,000 is our next one for year 30. Okay, same idea. And then year 40 is just over 110, so it's about in the middle. So then when you make your line, hopefully it looks like a little curve. Okay, so that's what your graph should look like. So now I'm going to have you try these last ones on your own. Okay, so E, F, and G. So if the population continues to increase at the same percentage rate, what would the population be in 2027? So you're going to do that one on your own and then check your answer. So go ahead and do that now. All right, so for E, you're going from 2003 when this started, when the population was recorded in 2003 to 2027, which is 24 years. So when you plug it in, you get 72,023.5 people. Can't have 0.5 of a person, so your answer here is going to be the 72,023. Okay, so again, same idea for F. Okay, if the population had been increasing at the same percentage rate since it was founded, what was the population in 1980? So it's telling you the town was founded in 1980. Okay, so I want you to really think about what that means. And see, I want to challenge you to see how you do with this one. Okay, so really think about it. All right, so for F, you're going from 2003 and you're trying to find the population in 1980, which is actually representing decay. So when you do your subtraction, you actually find that that's you're going backwards 23 years, so it has to be negative. Okay, so you're trying to find the original amount. If you just plugged in 23, you would have year 23 instead of 23 years ago. So that's why it has to be negative. So then you plug that into your function. You have a negative 23 up here. So when the town was founded, there were 20,590 people. Okay, so that one was a little tricky. That's a really good Regents type question. So make sure if you have questions on it, you ask. So last thing I want you to do is part G. Okay, so find M of 14 and then explain what this means in real life. All right, so this M of 14 means that A is year 14. So you're going to plug that in. So you get 55,178 people. And if you find what year 14 is, that's actually in 2017. So your brief explanation just needs to be this little bit right here. You need to be able to tell me what year that population was. All right, let me know if you have questions. Have a good day.